let's start. Thanks for all coming. It's my great pleasure to, now what is it now, the second year of the Geoclimate Seminar series. And the room is still full, which means we do something right here. And certainly what we do right is we have the right speakers. But before I introduce you another, I just wanted to remind you, kind of all those that have not been here, the point of these seminars here is that you ask questions and that you have interactions with the speaker, right? So please, if during the presentation, you're always welcome to ask and interact. We also usually keep discussing after the presentation, so please come up with any questions that you might have. The idea really is here to foster dialogue. With that, having said the brief organization, we will do it again through this seminar semester, every 2 weeks. We will send out again the flyers as in the past, because I will be for quite a while in Berkeley, and Nada will actually do the organization, so the emails may be coming from him. And with that, yeah, it's my great pleasure to introduce Nader. He's coming originally, he did his PhD with David Roms in Berkeley. He's then been a postdoc in the AOS program, and since more than a year now, he's a Hess Fellow in the Department of Geosciences, working with us on a range of problems from radiation, protection, basically everything. So it's my great pleasure to introduce Nader. Thank you.
Thank you. Yeah, so I'm very happy to talk about this work. So this is a lot of the work that I've been doing as a Hess Fellow, and in conjunction largely with Stefan and some other collaborators who are listed here. It's been great being a Hess Fellow in the Geosciences department. Having freedom to pursue my interests, support from great staff, and access to great minds. And this is what I've been doing, basically. So, so the motivation here is to, there's sort of, well, maybe the first thing I'll say is that when we talk about sometimes you read about, especially in the popular literature, like the greenhouse effect. And the theme of this talk is that the fact that we have greenhouse gases in the atmosphere, gases that absorb and emit infrared radiation, is multifaceted. There are many aspects and manifestations of the greenhouse effect. And so here's a little cartoon slide just to get a sense of that. So if we think about how energy flows throughout the atmosphere, right, throughout the Earth's system, rather, sunlight's coming in, getting absorbed by the ocean surface, heats the ocean surface up, it reaches a finite temperature, and so emits thermal radiation, but we have these greenhouse gases in the atmosphere, right, water vapor and CO2. So they absorb this upwelling, long wave or thermal infrared radiation, and they emit it back down. And in fact, these two arrows largely, but not perfectly, cancel. So the ocean surface, or more generally the Earth's surface, can't really cool very effectively by radiation. So what does it do? It does what we do. It sweats, right? It evaporates water, and then convection takes this water aloft, this water vapor aloft, where it condenses and releases this latent heat. And once you're aloft, then this latent heat can be radiated out to space. So you can see just from this simple cartoon that these greenhouse gases do a lot of different things, right? They absorb upwelling near the surface, they emit downwelling at the surface, and then they emit long-wave radiation to space, outgoing long-wave radiation. And then if you consider the atmospheric energy balance, right? So the energy budget not of the planet, but just of the atmosphere. Again, from this cartoon picture, you see that the atmosphere is heated by condensation from water vapor. And cooled by this greenhouse gas emission to space. So that then gives you a connection between precipitation on the one hand, right? Because any water vapor that condenses, if it re-evaporates the atmosphere, it doesn't provide a net heating to the atmosphere. So it actually has to fall out of the atmosphere to give a net heating to the atmosphere. So it's really the precipitation that heats the atmosphere. And the heating from precipitation, so I take the precipitation rate, I multiply by the latent heat of vaporization, that gives me something in watts per meter squared. It turns out that the atmospheric energy balance, that this precipitation heating is basically balanced by this long wave cooling. So there's actually a connection between the greenhouse effect and precipitation. So again, there's many aspects to the greenhouse effect. And so what I want to do in this talk is isolate a few aspects of the greenhouse effect that are well known and sort of pretty robustly simulated by models. but for which we don't often have like an easy or simple way of thinking about. So a few of these are the forcing you get by doubling CO2, which has a sort of global mean characteristic value of something like 4 watts per meter squared, and models don't disagree hugely on this. And of course, it's an extremely important number in terms of climate change. Also, this cooling of the atmosphere by greenhouse gases that we were talking about has a characteristic magnitude that tends to cool the atmosphere by roughly 2 Kelvin per day. And again, this is very robustly simulated by models. Another thing you find is that if you look at, in a global warming scenario, how the sort of global hydrological cycle changes, it turns out that the precipitation, when measured in watts per meter squared, changes by a few percent per Kelvin. And because it's connected to the total rate of cooling of the atmosphere, that also changes 2%. But again, we don't have sort of simple ways for explaining these numbers. So what I want to do in this talk is to try and put together some simple models for each of these quantities that'll give us a back-of-the-envelope way of estimating them. Because right now, I think if a student asked you, why is the CO2 forcing 4 watts per meter squared? I don't think we can explain it to them on a chalkboard. And that seems like a gap in our science that seems worth filling. And then hopefully, if we build a simple model and it seems like it's capturing the first order of physics, then maybe that'll actually give us some insight into what's happening. So that's the roadmap. So what are we actually going to do? So the main tool, one of the main tools we're going to use is a line-by-line radiation model. So this is a piece of software that calculates radiative transfer through the atmosphere at line by line, sort of as a function of wave number. So you sort of feed in the molecular spectroscopy of all your greenhouse gases, and it'll calculate it's sort of it's state of the art, and it's kind of a benchmark. There's sort of very little uncertainty about this calculation. What does it do? It calculates optical depths, which is something I'll talk about in a minute, and the upward and downward fluxes of radiation as a function of wave number. And we're going to do this. We're going to take a single column of that's kind of representative of the tropical atmosphere with typical sort of parameters. It's a typical surface temperature of 300 Kelvin, lapse rate of 7 Kelvin per kilometer. It's a typical relative humidity and a pre-industrial CO2 concentration. The other thing we're going to do is then we're going to try and emulate what this guy is doing with pencil and paper, and try and build some simple models. Of course, in doing this, approximations are going to be required. The first thing we're going to need is what you might call the unit optical depth approximation. So what does that mean? So what I've got here is a cartoon picture of greenhouse gas molecules. Picture here is water vapor molecules. So you think of this as a column of atmosphere, and the concentration of these guys is kind of increasing exponentially downward. And that's true both for water vapor and for CO2. For water vapor, that's a consequence of this Clausius-Clapeyron scaling of water vapor concentration. For CO2, it's just the fact that density increases exponentially downward. So how is this column going to radiate to space? So let's start at the top. So in this layer of the atmosphere, I've got a single molecule. It's got a clear view of space, so it cools, but there's not many molecules in here, so the total cooling in that layer is not very large. I go down to the next layer. I've got slightly more molecules. They've still got a clear view of space, so I get slightly more cooling. I go down to another layer. I've got more molecules still, and they still have a clear view of space, but just barely. So they're going to cool the space quite effectively. But then when I continue to go down even lower, the cooling starts to decline. I've got more molecules. I've got even a higher density of molecules, but their view is obstructed. They bought the cheap seats, right? They can't see space. And so the cooling is going to start to decline. And even more so for these guys. They're in the nosebleeds, right? They can't see it. So we can formalize this, this sort of cartoon picture here, with this notion of optical depth. This is sort of a fundamental quantity in radiation physics. And there's a simple formula for it. It's just that at any height z, the optical depth is just your absorption coefficient, which is just the effective area, that you can kind of think of as an effective cross-sectional area, of your molecule per unit mass, so meter squared per kilogram, multiplied by this integral, where I'm just integrating the density of my absorber with height above me. So I'm integrating from z to infinity. The units of this is kilograms per meter squared, right? So the kilograms of absorber above me. So if I multiply these two guys together, I get something dimensionless, right? What is its interpretation? Well, this is the effective area of absorbers above me per unit mass, and this is the mass of absorbers above me per unit geometric area. So this is just the total effective area of the absorbers above me divided by my actual area. This can be much less than 1, much greater than 1, or about 1. And so that actually separates what we're seeing in this column into a few regimes. So up here, my optical depth is less than 1. I've got a clear view of space. My effective area is less than the actual area, and we say it's optically thin. Down here, the effective area of absorbers above me is greater than my actual area. My view of space is blocked, and we say that's optically thin. And then here, it's sort of your Goldilocks regime, and it's just right. You have a good number of absorbers, but you also have a clear view of space, and so that's where you're going to emit from. So this unit optical depth approximation is saying that if you want to emit radiation to space, the best place to do it at is from optical depth 1. So this is sort of a key piece of physics in most of what follows. All right, so that was a cartoon picture. How does this actually play out? So now I want to show you some plots from this line-by-line radiation code. So the first thing the code does is it takes in spectroscopic data, and it computes the absorption coefficients. So this is absorption coefficient kappa, meters squared per kilogram, plotted logarithmically on the vertical axis as a function of wave number. Wave number is proportional to frequency, so if you'd rather think in terms of frequency, just multiply this by the speed of light. And so you see these features, and this absorption here is due to water vapor, and the absorption coefficient is high, so the water vapor molecule appears large. Over here in this part of frequency space, there's absorption, but the absorption is weaker. The water vapor molecule appears smaller, has a lower absorption coefficient. And this big spike here is from CO2. Right? All right, and so this is output from this numerical model. This numerical model also computes the optical depth, which again, I'm showing here, it's plotted logarithmically. And you see there's a huge variation in the logarithm of optical depth. So there's just a huge variation across the atmosphere in the vertical and also wave number space of how optically thick the atmosphere is. And this dashed line is where the optical depth is equal to 1, so or the log is equal to 0. Right? This is our unit optical depth level as a function of wave number. And then this plot is the cooling to space. So what is that? It's the watts per meter squared of emission per unit depth, measured here in pressure, hectopascal, per unit frequency interval. Right? And again, you see that the distribution of this follows very closely this tau equals 1 log. Right? So the model is doing this. It is emitting roughly from unit optical depth. Right? And of course, it's not perfect. There is some spread in the vertical, but clearly it's following, this cooling is following these contours. So what we're going to do is we're going to use this idea that we can think of the cooling as basically all emanating from this contour to build a simple model for CO2 forcing. So how are we going to proceed? So the first step is to take these absorption coefficients, this optical depth, and try and make it a bit simpler. So again, this is what you get from this line-by-line radiation code. And what I've done here is I'm focusing on the CO2. I got rid of the water vapor, so now there's no more water vapor in this calculation. And I've zoomed in on the CO2 band. So this range of wave numbers is much smaller than what I was showing you in the previous plots. This is just the CO2 peak here. The other thing I've done is that when I plotted this, I've smoothed out this curve. If I actually plotted all the features, you'd see a lot of wiggles. And then I've just sort of binned everything in bins of width like 10 inverse centimeters and just smoothed over that to kind of expose the underlying structure and get rid of what you might think of as noise, although you do lose something when you do that. We can talk about that. But so here's your smooth absorption spectrum from the model. Here's the optical depth. And the dashed line is again your optical depth equal 1 contour. And so you look at this, and again it's plotted in log coordinates, and you think, boy, that just looks like a triangle. Kind of looks like a straight line. So why don't I just model it as a straight line, right? So I literally just make a linear fit to this. Of course, this is logarithmic, so it's actually an exponential, right? And I get a few parameters out of this fit. I get the center of the CO2 band, the wave number, that's K0. I get the absorption coefficient there, kappa 0. And then this LK parameter here, which is going to turn out to be key, is just the inverse of the slope of this curve. And that's going to be a central parameter in what follows. And the other thing I can do is I can take that expression for optical depth that I have, that was this integral, right? I'm just integrating the mass of the absorber above me. And I get this expression. And then I can plot that with this analytical form of the absorption coefficient. And it gives me this. And again, it's idealized, but it looks like it captures to first order the behavior of what the sort of more comprehensive line-by-line code is doing. Right. All right, so now that we have some simple formula here, let's try and build a theory for the CO2 forcing. So again, we want to know what is CO2 forcing. It's just the change in the top of atmosphere radiation when I double or quadruple CO2, when I change the CO2. So I want to think about these emission levels and how they're changing with CO2 concentrations. So the first thing I do is I take this expression for optical depth. I set it equal to 1, because I'm interested in the levels of unit optical depth. So I set it equal to 1, and I solve for the pressure. So that's just algebra. And then I plot this. And it gives me just the same triangle that you saw in the previous plot. And by the way, this coefficient out front, which I'm calling P0, is just the pressure from which the center of the CO2 band emits. It's sort of a characteristic pressure for CO2 at a given concentration. It turns out to be something like 30 hectopascal for pre-industrial concentration of CO2. And so now you can ask, right, so remember, this is for each wave number, it's the height in the atmosphere from which CO2 is emitted to space. Right? That's what we're showing. So now you ask, how does this picture change if I, say, quadruple CO2? But now I've got the simple formula, so I just put a 4 in here, and this is what I get. And I've color-coded it. I'm going to explain that in a second. And so now I want to ask, OK, if I know these are the old and new emission levels, how does the total emission at the top of the atmosphere change? Now, the way that people usually do it, and the way that it's done in radiation code, is you do the calculation again, line by line, wave number by wave number. Where I say, oh, my old wave number, I was emitting from this level. Now I'm emitting from up here, and it's a little colder up there because temperatures are decreasing as I go up. And so that decrease in radiation is my forcing, and so you add it up for each wave number. That's how it's typically done. There's actually a simpler way to do it that I think gives us a little more insight. And that's to do it, instead of wave number by wave number, let's do it level by level. So let's, oh, and the other thing I should mention is that the width, the difference in width of these two triangles, you can compute it from this, and it turns out to be this LK parameter, right, which was the inverse slope of this curve, which has units of inverse centimeters, times the log of the ratio of the CO2 forcings. So it just comes out of this math, but we all know that the CO2 forcing is logarithmic in the concentration, right? So you're starting to see hints of that just from this simple theory. And I'll say a little bit more about that as we go on. All right, so we want to use this to derive a formula for CO2 forcing. How do we do it? So let's start at the top. So if I look at this level, when I had my pre-industrial concentration, the solid line, there was no CO2 forcing up. There was no emission from CO2 up here. When I quadruple CO2, there is. So I'm actually adding new emission in the stratosphere. That actually increases the radiation out to space. So that's a negative forcing, right? Taken by itself, that would actually cool the planet. And in fact, it does cool the stratosphere. And many of you know that the stratosphere cools when you add CO2. And this is one way of understanding that, right? That there's levels of the atmosphere that weren't emitting before, but are when you increase the CO2 values. Now let's look at the orange part of these two curves. Well, so I don't know, let's take this 100 hectopascal level. So for pre-industrial CO2, I was emitting from here. When I quadruple it, I'm still emitting from this level, but at a slightly different wave number. But this wave number difference is so small, the Planck function, which governs emission, is hardly varying if I change the wave number of my emission. So really, the emission from this level is not changing when I double CO2. Because remember, this is an instantaneous forcing. I'm not changing the temperature of the column. I'm not letting the system warm up yet. I'm saying if I just quadruple the CO2, I'm just asking instantaneously, how does the radiation at the top of the atmosphere change? So the temperature of this level hasn't changed, the wave numbers barely changed, so the emission hasn't changed. So the surprising thing that this picture is telling you is that this whole portion of the atmosphere does not contribute to the forcing. There is no tropospheric contribution. To first order, there's no tropospheric contribution to the CO2 forcing. So that's odd. I'm saying I get a negative contribution to the forcing here, which would actually cool the planet, and no contribution from here. So where is there a positive contribution from? It's from the surface, right? So if I look at this little highlighted red blob, that's the part of the surface which had a clear view of space and was emitting to space with my pre-industrial concentration, But once I quadruple CO2 is not emitting to space. The tau equals 1 level was underground before, but now it's up here, right, at this frequency. So this emission from the surface is blocked, and this contributes a positive, this makes a positive contribution to the CO2 source. And so it's funny, it's almost like this sort of cartoon picture that you might tell to a beginning, a sort of introductory climate class that, oh, what greenhouse gases do is they block surface emission and replace it with colder atmospheric emission. That's exactly true here. You just have to evaluate it at the right level. Right? It turns out to be in the stratosphere. So with this picture and with this expression for delta K, I can actually just write down an expression for the CO2 forcing, right? Because I just want to say that the forcing, there's a positive contribution from this, which is just the Planck function at the surface, times the width of this region, which I know is LK log 4, times 2, because there's two sides to the CO2 band. And then I get a negative contribution from the stratosphere. And so this formula is both telling us that the CO2 forcing is logarithmic, which we sort of know from complicated model runs, but this is giving us a simple derivation of that. And it only depends on the temperature contrast between the surface and the stratosphere. Those are the only temperatures that matter. I could wiggle the temperatures around the troposphere and it actually wouldn't change the CO2 forcing. And this has sort of funny manifestations. So a few papers have been published showing that over Antarctica, where the surface is actually colder than the stratosphere, you actually get a negative instantaneous greenhouse effect over Antarctica. Now, that doesn't actually end up cooling Antarctica because once you let the stratosphere adjust, this temperature gets colder, and actually ends up getting cold on the surface, and the adjusted warming is positive. But instantaneously, it's true. Yeah, question?
Yeah, just want to make sure. Before quadrupling CO2, is the surface that wavelength blocked by water vapor bands, or no?
Yes. So this picture is a CO2 only picture, and you do have to modify it in the presence of water vapor, but which you can. Right. So if you had water vapor emission, you'd have sort of emission from water vapor that looks like that, the emission heights. And so then this picture remains, but instead of blocking surface emission, you're blocking water vapor emission from a colder temperature. So you just have to replace the surface temperature with the appropriate water vapor emission temperature. And if you're wondering why is this logarithmic, you can actually get that from this. If I say quadruple Q, right, but I still want to know where tau equals 1 is, then I have to just move to a K where kappa is 4 times larger. But remember, kappa is exponential in K, right? So then I just need to move K over log 4, right? And so that means this sort of, the width of the CO2 band must be logarithmic. And it just comes from this expression, the fact that kappa and Q multiply each other, and kappa is exponential in K. All right, so we've got this formula. It sort of seems too good to be true, right? It's so simple. I literally like drew you a cartoon and then wrote down a formula. Is it too good to be true? It is and it isn't. So let's talk about what it can do. So we want to test it. So I'll take my idealized tropical column, just my single column that I'm going to run through the line-by-line radiation code. But one thing I'm going to do is I'm going to vary the surface temperature, right? Just to get a number of different cases that I can then test this formula on. And I should say that it's CO2 only, and I'll talk about the effects of water vapor in a second. So this is what you get. So I run my line-by-line radiation code, and that's plotted on the horizontal axis. And then I take these columns and I just diagnose the surface temperature and the appropriate stratospheric temperature, feed that into the formula, and that's what's plotted here. And then the black line is the 1-to-1 line, right? So if the theory was perfect, all the dots would lie on the exactly on the 1-to-1 line. And it's not perfect, but it's not bad, right? So this is telling you that it looks like this formula is capturing the first order physics. Of course, there's many caveats, right? This is clear sky only. There's no clouds. Right? And we know that clouds do have an effect. There's no water vapor. And as Sunmin just pointed out, there are effects of overlap with water vapor, which especially in the deep tropics can be quite significant and can change the forcing by a few watts per meter squared. The atmospheres that I was testing this on are very idealized. It's got an isothermal stratosphere and a constant lapse rate. Also, there's no stratospheric adjustment. So usually when IPCC and others report the forcing from CO2, they give the stratosphere a couple months to change temperature, and then that actually changes the value of the forcing, and that's what's most relevant for the coupled troposphere and surface system. So this really is just a first stab at understanding the CO2 forcing. But these effects, they do matter, and they're not negligible, but they don't seem to change the sort of first order estimate. Like this is sort of, this determines the order of magnitude of the CO2 forcing. And then you need to take all these things into account to get something more accurate. So what that means is that we should be able to use this to get a back of the envelope estimate. So let's do that. So let's do it for a doubling of CO2 forcing, because we expect that number to be about 4 watts per meter squared. So I've got a log 2 here instead of a log 4. So let me just plug in a globally average surface temperature of 288 Kelvin, and a globally average stratospheric temperature, where, again, the stratospheric temperature is this pressure that was determined by the emitting pressure at the center of the CO2 band. Right? That's what I mean by a stratospheric temperature. This is this Planck function evaluated at those temperatures. So 0.4 watts per meter squared per inch per centimeter, 0.15, so the difference is 0.25, 0.25 times 15 is about 3.7. So right in the ballpark. And again, it's just a first order estimate. Those corrections that I talked about would, change this plus or minus 1 or 2, but it's getting in the ballpark. All right. So it's one of our tasks. So we succeeded in constructing a simple model, and it looks like it both reproduces some familiar aspects of the CO2 forcing and also provides some insights which were surprising to us, right? And other papers have been published saying, oh, if you read the literature about the CO2 forcing, there's an awareness that, of course, the temperature contrast between the surface and the atmosphere is important, but it's sort of fuzzy about where in the atmosphere you have to worry about the temperatures, and this gives you something actually a bit more precise. So that sort of concludes this first, I guess, third of the talk. Any questions on that before we move on?
So, I mean, that temperature difference will depend on water vapor, right? I mean,
Yes, yeah, that's right.
And the water vapor will depend on temperature. So, a mean temperature, right? So the concentrate, or not.
Not. It yields a temperature, but it is independent of the surface temperature, right? So it turns out that the water vapor, the emission temperature from water vapor, it's slightly different on the two sides of the CO2 band, and there is a sensitivity to relative humidity, right? And so those are things that are going to cause it to change, but they're basically in the 280 Kelvin ballpark, and it's hard to change it to values much different than that. So basically, what you would do to modify this formula in the presence of water vapor is you would just, instead of putting in the surface temperature here, you put in the minimum of the surface temperature and the characteristic water vapor temperature.
So for high latitudes, it's going to be less than 280, so that the surface.
Exactly.
And the low latitudes, it's
exactly. Exactly. That's right. And so we have extended this work to include water vapor, not showing the plots, but it's there. And so in our simple model where the sort of water vapor is on or off, you get the sort of unrealistic discrete thing where you're either seeing the water vapor emission or you're not. And of course, the more realistic calculation is more gradual. But I think the first order, that's what happens. All right. So another aspect of the greenhouse effect that is sort of familiar, but maybe we don't have an intuitive feel for, is atmospheric radiative cooling, which has this characteristic value of 2 Kelvin per day. And this value is surprisingly robust. So what's shown here is a distribution of radiative heating rates as a function of latitude and pressure. So these are zonal means from ECMWF reanalysis, which, if you're not familiar with reanalysis, is essentially model interpolated observations. You run a radiation code on these profiles, and you get heating rates, and we average them over longitude, and this is what we get. And so you see it's just basically this blue blob. And there's some structure, but it really does seem kind of clustered around 2 Kelvin per day, minus 2 Kelvin per day. And then if I take a zonal mean, or sorry, yeah, that's right. So then if I average over latitude, and I'm just left with the vertical dimension, then this is the heating profile I get. And remarkably uniform in the vertical, up until you get to near the tropopause at 2 Kelvin per day. And interestingly enough, you can actually emulate this pretty successfully with just this single tropical column. And I'll do this with actually water vapor only, and actually emitting the water vapor continuum, and we can talk about those emissions if people are interested. But so if I take my tropical column and do this calculation, I get that. So again, so it's pretty robust, right? I can take like a global average, or I can just do one tropical column, and I still get this 2 Kelvin per day. Very similar value and pretty uniformly vertical. Yes, Max?
So I just did you say you average about all latitudes for the radiative heating profile here?
So this is just the zonal mean of, not zonal mean, average over latitude. This is just average over latitude of that.
So in the polar vortex, you mean the cooling is offsets the heating in the tropics, in the stratosphere? Because I'm just sort of surprised to see it like bifurcating that much in the stratosphere, basically. But that's probably just me, actually.
You're asking about this stratospheric heating distribution?
Yeah, I mean, the tropics normally is supposed to heat, and I was expecting that it would not sum up to such negative values in the stratosphere. That's why I was just surprised.
Are you talking about these negative,
or in the profile if you want.
This blue up here, the cooling, up there? Or are you talking about the heating right around the tropopause?
Or maybe. Yeah, I mean, there's okay.
Well, we can look at the plot at the top. All right. So yeah, so there's something really robust about this number. So where does it come from? Why is it so robust? Why is it so robust? How can we understand it? So in addition to the unit optical depth approximation, we're going to employ another approximation called the cooling to space approximation. So what is that? So here what I've done is I've taken that same single tropical column calculation of the cooling, and I've spectrally resolved it. So you're looking at the cooling as a function of pressure and wave number, so it's Kelvin per day per inverse centimeter. And you see that it's concentrated along this this one band, this one water vapor band. And what have I calculated here? I've calculated this heating rate, spectrally resolved, and it's really a flux divergence. And sometimes we don't always realize that a heating rate is really a flux divergence in pressure coordinates, and then you multiply by some constants to get something in the units of kelvins per day. And the choice of coordinate here of pressure is to a certain degree arbitrary. I could also take a derivative with respect to, say, height, right? And we'll come back to this choice of coordinate later. All right, so this is the thing. So we're interested in the spectral integral of this, but to understand it, we need to spectrally resolve it. And it looks like this. But the picture I painted for you at the beginning of the talk was that this cooling comes from these molecules emitting radiation to space, generating OLR. But that's not all, in principle, that's not all the cooling, right? You could have cooling at certain levels, not just by emitting radiation to space, but also by exchanging radiation with other parts of the atmosphere, right? So there's other terms in the radiative heating besides emission to space. You can have radiative exchange with other layers. But it turns out that this cooling to space term is the dominant term. And so if I compute just the cooling to space term, it looks like that. So you almost can't, I mean, for just water vapor, you'd be hard pressed to tell the difference. If I put CO2 in here, there'd be some features that look slightly different. But for just water vapor, it's almost impossible to tell. So what is this cooling to space? It's not a flux divergence. It's something a little bit different. It's the Planck emission times your emissivity gradient, which is just the concentration of absorbers, times the transmissivity, which is just your view of space, right? So these terms just encapsulate the physics that I talked about in that first cartoon, and it's this combination of factors that maximizes a tau equal 1. The reason this is important is because to get the flux divergence, I have to actually do an integral to compute the flux downward, an integral to compute the upward flux, an integral to compute the downward flux. This is then the net flux, the difference between the upwards and downwards, and you have to take the derivative of it. So there's a lot of calculation involved in this, and a lot of integration. This, once you know the optical depth, you can just compute this, right? So it's actually much simpler to compute. In fact, the GFDL homegrown radiation code uses this approximation as sort of the basis for its radiation calculation, and then adds correction terms. So we're going to lean on this to try and build a simple model for radiative cooling from water. All right. So we're going to sort of take a similar approach in that we're going to try and simplify what the line-by-line code is doing. So here's shown the absorption spectrum of water vapor. So again, absorption coefficient on the vertical, frequency on the horizontal. There's sort of two bands. This is called the sort of rotation band, and this is the vibrational rotational band. That's to do with the molecular spectroscopy. Here's the optical depth distribution, and again, of course, the shape of this, the shape of the tau equals 1 line follows the shape of the absorption spectrum, right? Because where absorption is strong, I don't have to go as deep in the atmosphere to get tau equals 1. And then here's a cooling to space, and again, following the same shape. If you look closely, you can see some cooling associated with this band, but the Planck function is declining here, right? So even though there's tau equals 1 levels, at terrestrial temperatures, you just don't get enough emission. If you were hotter, you would, right? But terrestrial temperatures, you don't. So we're going to kind of neglect emission from here on out. So again, if you look at this absorption spectrum, it kind of looks linear if you sort of smooth over the wiggles, right? We're going to play the same game. We're just going to make a straight line fit. And you can do it for both, but I've just written down the expression that you get for this band, because that's what's important. This is the optical depth distribution you get. So again, I do this integral for the optical depth. I'm integrating all the absorber above me. So that's just the absorption coefficient. This is a pressure broadening coefficient, which we don't need to worry about, and it's sort of not a dominant effect. And this is just the water vapor path. So it's just the kilograms per meter squared of water vapor molecules above you. And you see that because the density of water vapor has a Clausius-Klaproth dependence, right? It's just a function of temperature with this L over RVT. The water vapor path has that too. This is going to be key for what follows. Moreover, you see that this optical depth distribution, again, to first order seems to capture the behavior that you get from the comprehensive model. And here is the cooling using the cooling to space approximation and also plugging in these analytical formula for the optical depth. Right? And so, it's definitely an approximation. This cooling seems to have a larger magnitude than here. It's actually because I smoothed over the wiggles, the cooling is more confined in the vertical. Here it's a little bit more distributed, but the actual vertical integrals are comparable. So I've just sort of changed the distribution of this cooling in the vertical. But it's not once you integrate in the vertical, you don't get the wrong magnitude of cooling. All right. Yeah, and the way I've sort of presented this plot, I've sort of tried to construct a simple model that sort of all along the way emulates what the more comprehensive model is doing, so that hopefully, if we just to make it believable, right? So that we trust what it might be telling. And this was a topic that we explored in a commentary in James a couple years ago. All right, so we were interested in this 2 Kelvin per day number, and what we have here is a distribution, especially resolved distribution of cooling. So what we want is especially integrated cooling, so we want to do the integral over K, right? Which will just yield a vertical profile of cooling. So we've got the simple expression, and now the question is, can we do the spectral interval? Can we integrate over K? So what we're going to do, we're going to play a few tricks. So the first thing that we do is we take, remember this is this emissivity gradient, right? And it's basically proportional to your concentration of absorbers. And I'm going to write it instead of d tau k dp as d log tau k dp, and I'm going to put an extra factor of tau k over here. So it's just a mathematical trick, right? But the point is that then if I plug in that analytical expression that I had for tau k, then I get something of the form beta over p, where beta is not quite constant, but it's pretty close to constant. It's a dimensionless number. It varies by maybe 50% over the course of the atmosphere. And rough value is about 5. Okay? And then this expression here, well, it's interesting. It's the function x times e to the minus x. Well, that function integrates to 1 and has a peak at 1, right? Sometimes it's called a weighting function. But you can also approximate that as a delta function, right? It's basically a function that has a peak and integrates to 1. That's what a delta function does. You're just collapsing everything to a specific value. And that's exactly the unit optical depth approximation, right? If I take this smooth function that has a peak at 1 and collapse it to a spike at 1, I'm saying everything's happening at tau equals 1. That is the unit optical depth approximation. The other thing I'm going to do is I'm change coordinates from k to tau k, right? So if I look back at this at optical depth, it's both a function of height and of k, and so I can actually change my horizontal coordinate, my spectral coordinate, from k to tau k. So that's what I'm doing in this step. When I make that change of coordinates, I pull down a factor of Lk, which remember it came from the spectroscopy. It was the slope at which the absorption coefficients declined with Wigner. And it has the right units of inverse centimeters. So then I sort of massaged this expression in that way and got this delta function. Well, integrating over a delta function is trivial, right? The delta function is peaked at some value, and what I get is just an integrand evaluated at that value. So that gives me this, right? I have my beta over p, I've got my Planck function, I've got my Lk, and the Planck function I just have to evaluate where tau equals 1. So I get this k1, so what is k1? It's just, this thing is a function of height, and at each height, there's a function k1 that tells me what wave number is emitting to space at that height. And you can get an analytical expression for this just by taking my analytical expression for tau, setting it equal to 1, and solving for k. So I'm not showing you the analytical expression, but it's there. So this now finally is just a, gives you a profile of cooling. Right, and it's worth interpreting the different factors here. So we've got the Planck function, this beta over p, remember, is the emissivity gradient and pressure coordinates. And this Lk has units of inverse centimeters, and it gives the effective width over which any level is emitting to space. So let's test it. So this is the plot that I showed you before of a global distribution of heating rates and then the global average. So what I can do is and then I also have what I got from my single tropical column run through the line-by-line radiation code. So I can take that single tropical column, I can compute K1, and I can just feed K1 and the temperature and pressure profiles into this, right? So what do I get? I get that, the gray one. So it's not perfect, but it definitely seems to have a characteristic value of about 2. And it even gets this little kink up at the top of the atmosphere, which is relevant for things like the fat hypothesis and anvil clouds and things like that, which we can discuss in the Q&A if people wish. So this suggests that at least a first order, we're getting physics right. So the next thing we can do is make a back-of-the-envelope estimate, because now we have a simple formula. So here's our formula, constants, Planck emission, the width, the characteristic width over which you're emitting at any given height, and then this emissivity gradient. So let's plug in some numbers. So for the Planck emission, it's 20 watts per meter squared. That's integrated over this characteristic spectral width. This is the emission that you would get over a sort of atmospheric layer of depth 100 hectopascal, which I got by plugging in beta equals 5 and evaluating this at, say, 500 hectopascal, just kind of the middle of the atmosphere. So 20 watts per meter squared per 100 hectopascal. And then these constants here you can just see as converting from a flux divergence and pressure coordinates to a heating rate. Well, so this is really just 20 times 10 to the minus 6. That's 2 times 10 to the minus 5 kelvins per second. But there's about 10 to the 5 seconds per day. So that's about 2 Kelvin per day. Yeah?
So you said this 2 Kelvin per day is uniform across latitudes. But different latitudes have different temperature, surface temperatures. So
surface temperatures, right? So the surface temperature doesn't enter into here, but you're saying at a fixed pressure, on a fixed pressure, you'd still also get changes in temperature. Right? So that's quite interesting. So if I look at looking at this expression, what's varying in the vertical, right? This expression is varying. It's actually decreasing as I go up because temperatures are going down and because I'm moving to lower wave numbers, right? This expression is actually going up because as I move upwards, the frequencies that are emitting are the ones that are more strongly absorbing, and they have stronger emission gradients. And it turns out that these effects actually kind of coincidentally kind of cancel out, which is why you get this uniformity in the vertical. But of course, this uniformity in the vertical for different temperatures also extends to uniformity in the horizontal. But I think it's largely, I think that is largely coincidental. And so this is another point. If I compute flux divergence in a different set of coordinates, say in z coordinates, the cooling is not uniform in the vertical.
So what does that tell you?
What's the significance of that? I think it depends on the question you're trying to ask. So in the last part of the talk, I'll talk about looking at cooling rates and temperature coordinates, and it's not uniform, and there are implications. The fact that it is uniform in pressure coordinates, I don't know if there's an important consequence from that. It could be. I'm not. Do you have something in mind?
No, I'm just,
Yeah.
I can't put my finger on it, but there's something.
Yeah, could be. Yes?
I mean, the significance is that basically the atmosphere is uniformly subsiding. I mean, the pressure is mass. So the cooling per kilogram. So that's a very, very physical thing, much more than, say, per kilometer or something.
Yeah.
Right? So what it says is sort of to leading approximation, you can think of the air subsiding everywhere at roughly the same rate, which also says that you don't have much secondary circulation within the troposphere. Because if the cooling rate was very different as function of height, and that's happened when you have a cloud, for example, right? When you have a strong gradient in heating and cooling rate, that is always associated with turbulence. So it basically says the atmosphere in itself is not turbulent. So a little bit to the...
But that's the troposphere. It's not turbulent. Is that the implication?
It's not, or the turbulence, not for that. The turbulence is not forced by a radiative cooling gradient.
Right.
But it's really coming from the surface.
Yeah, so that's a good example of, right, so if you think about circulation, then I do think it makes sense to think in pressure coordinates. And then, yes, you do have this consequence. Yeah. All right, so returning to our sort of outline here. So we have a simple model for the atmospheric radiative cooling. It can reproduce this 2 Kelvin per day number. And these factors sort of have a simple interpretation. This is the emission per unit spectral width. But then you have to multiply that by an emissivity gradient, and then by characteristic spectral width. And that gives you your flux divergence and therefore your cooling rate. And so then the last topic is this green precipitation change, which I spoke about a couple years ago when I was interviewing for the HES. So some of you may have heard this, but it sort of fits into this framework, so I'll spend maybe the last 10 minutes of the talk telling this story. So again, this is another aspect of the greenhouse effect, right? So the fact that radiative cooling is balanced by precipitation means that if you understand how the total column radiative cooling is changing, you can actually say something about how total precipitation is changing. And again, there's sort of a characteristic number that models robustly predict, which is that the fractional change in the total radiative cooling of the atmosphere, which I call Q, its fractional change with surface temperature is about 2% per Kelvin. And again, global climate models show this, sort of more restricted, limited area models show this, but there's not a great understanding of where this number comes from or why this is. So to get some traction on this, we'll turn to this expression that we have for the water vapor obstacle depth. And we note that, so I mean, there is this pressure factor here that comes from pressure broadening, and this varies by a factor of maybe 10. Right, as you go from the bottom of the troposphere, from the surface to the tropopause, your pressures vary by a factor of about 10. This exponential function varies by a factor of about 10,000. Right? So the optical depth profiles of all wave numbers are dominated by their temperature dependence. But this heating rate was a flux divergence in pressure coordinates. So it sort of leads one to ask the question, what if I change the temperature coordinates and then combine that with the cooling to space approximation? Then I get this expression. So this is the same expression that we saw before, but instead of taking my emissivity gradient with respect to pressure, I take it with respect to temperature. And that's important because tau is largely just a function of temperature. And the Planck function, well, it's a function of K1, which remember gives you the wave number that's emitting at any level, but that itself is largely a function of temperature, because I'm just inverting this formula for K, right, to get it. And then the Planck function has an explicit temperature dependence. So everything here seems to really just care about temperature. And the sort of, the visceral sense you should have about that is that water vapor is the dominant greenhouse gas, its concentration is governed by temperature, and then its emission is governed by its temperature by the Planck function. Those are the two main ingredients. So absolute temperature really is the thing that water vapor greenhouse effect cares about. All right, so this thing depends entirely on temperature. So what's the consequence of that? Well, let's take our tropical column and at various surface temperatures, and let's plot the flux divergence in temperature coordinates. And again, this is a single tropical column, water vapor only. So here's what I get for this flux divergence in temperature coordinates. Oh, and by the way, I'm applying this as a function of temperature, using temperature as my vertical coordinate, so increasing downwards just the way it does in the real atmosphere. And this is directly from the line-by-line model. This is using that analytical expression that we just derived, and they look comparable, which is good. And now what happens if I raise the surface temperature? Well, that expression that I just showed you, the surface temperature didn't appear anywhere in there. And so you can, and this curve is really just a graph of that simple function. So if I increase the surface temperature, I should be getting the same graph, the same curve, it should just extend a little bit further down. And that's indeed what you find, both in the line-by-line model and, of course, with the theory. And I can increase the surface temperature again, same story, again, same story. So there's sort of a universal curve, and as I increase the surface temperature, I'm just sort of getting to see more of it down at the bottom. Okay, well that's a neat fact. Why does it matter? It matters because remember, we were interested in the total column integrated cooling because that was connected to precipitation, right, by this atmospheric energy balance. And so, and if I have my flux divergence, this is sort of a schematic of my flux divergence plotted on the horizontal, and then temperature is a vertical coordinate, and this is just sort of a crude, straight line, imitating the profiles. I switched signs here, by the way. So instead of DTF, I have minus DTF, so now these values are positive. Hopefully that's not too confusing. And so Q, the total cooling, is just the integral. But since I'm doing a flux divergence in temperature coordinates, and I'm using temperature as my vertical axis, that's literally just the area under this curve. So we want to know how this changes with surface temperature, because that'll tell us how precipitation is changing with surface temperature. So let's draw this diagram again, but for a column with an increased surface temperature. Well, I get the same curve. The curve doesn't change. That's what I showed you in the last slide. And I just get to see more of it. And I could extend this down kind of, I could extend it diagonally down or straight down. It doesn't really matter as long as delta TS is small. So for simplicity, I'm just drawing it straight down. And now we ask, what's the new temperature, what's the new area under the curve? Well, the new area under the curve is just the old area under the curve plus this rectangle. But the dimensions of that rectangle are easy enough to reckon. So if I take delta Q, that area, and divide by delta TS, which is a finite difference approximation to this derivative, that's just the area of the triangle divided by one dimension, is just the other dimension, which is just the magnitude of the flux divergence evaluated at the surface. So the rate at which the column integrated cooling and hence the precipitation changes in surface temperature is just this. It's just the flux divergence in temperature coordinates evaluated at the surface, both in units of watts per meter squared per Kelvin. All right, so that's a simple formula for how radiative cooling and precipitation should change with surface temperature, and we want to test it, just like we did for our other simple formulas. I'm going to switch gears here now, though, and test it in a slightly different venue. Because what we're exploring now is this connection between the radiation on one hand and the convection in the other, which we sometimes refer to as a radiative convective equilibrium. Right? Radiative cooling is balanced by convective heating, which manifests as precipitation. And so what we can do is actually evaluate this formula in a model. Instead of just using my single column model, which just does the radiation side, you can use a model which sort of explicitly simulates both sides of this balance. And this is a limited area cloud resolving model. So what is this? It's a sort of fluid dynamical model of just a box of a tropical atmosphere. It's coupled to a radiation code similar to the code that I'm using. So it gives you sort of realistic radiative cooling as a function of the water vapor and CO2 concentrations. And I'll play this movie just to give you a sense of what this does. These colors near the surface just represent cold pools of air that are sort of spreading out that are produced by rain evaporation. I actually spent a lot of my PhD studying those. It's not important for this talk. But the point is just you have radiative cooling aloft, and then you have heat and moisture coming off the surface, and convection is lofting that heat and moisture up to where it can radiate up to space. But the point is that this model explicitly simulates both the radiative cooling and the convection and precipitation. So we're going to make use of all that data. So we've got this simple formula for how the radiative cooling and hence the precipitation should change. So how does it do? So what I'm going to plot here is I'm going to run those simulations that you saw, these cloud resolving simulations, at 4 different surface temperatures. And on the vertical axis, I'm going to plot the integrated cooling and the precipitation all in watts per meter squared. So this is the radiative cooling diagnosed directly from the simulation. That's the precipitation diagnosed directly from the simulation. And you see that this constraint that they're equal holds really quite well, at least over a certain temperature range. As you get colder, it starts to break down because actually the direct sensible heating of the atmosphere by the warm surface starts to take over. Because the warm ocean surface can directly heat the atmosphere in addition to evaporating the water. This formula is really a prediction for the slope of this curve. And the advantage of this formula is both that it's simple, but also that it can tell you the slope of this curve if you just give it one simulation. Right? Otherwise, you need 2 simulations and you have to draw the line between them. But this is saying just give me 1 simulation and I'll tell you the slope. So what is that slope? So the red lines plot that slope. And this formula seems to do pretty well. Up here it might look like it's starting to generate some errors. But actually this flattening out of precipitation as a function of surface temperature is real. And it's related to something called the runaway greenhouse effect. And again, we can talk about that. All right. So this formula seems to be capturing what the model is doing. So again, sort of repeating this theme, can we use it to make a back of the envelope calculation? So we were interested in the logarithmic change of precipitation, the fractional change in precipitation with surface temperature. We want to evaluate it at a typical tropical surface temperature of 300 Kelvin. So this radiative constraint of precipitation says that I can replace the P's with Q's, so I do that here. And then this formula is saying this dq dTs, I can replace it with the dTf. Again, I'll evaluate at 300K. And then, I should have pointed this out when I showed you the profiles of dTf, but a typical value near the surface is about 3 watts per meter squared per Kelvin. And for then this denominator, I can just read that right off this plot. It's about 100 watts per meter squared. So that gives me 3 watts per meter squared per Kelvin over 100 watts per meter squared. So that's about 3% per Kelvin. So it's just what the global climate model simulates. It's what this model simulates as well. So we have a back of the envelope way of calculating this. So that's nice, but it doesn't actually give us a tremendous amount of insight. So we were still wondering, the question that started this was why 3% per Kelvin? This gives us a simpler way of calculating it just from the baseline, but can actually yield some more insight into where this number comes from. And I think that it can. So here's a way of thinking about it. So let's take this flux divergence profile. So here's my dTf as a function of temperature, diagnosed directly from the cloud resolving simulation. And again, you see it's sort of increasing. And I don't know, if you were going to sort of like crudely parameterize this curve, maybe it'd be linear or maybe it'd be quadratic, something like that. And it goes to 0 at the tropopause, which has a characteristic temperature of about 180. And this temperature is actually the same in all the simulations, which is sort of a crucial feature of the simulations and of the and it's a behavior that's also reproduced in GCMs. So if we want to parameterize this, let's say, okay, the flux divergence is, temperature minus tropopause temperature to some exponent, and the exponent is maybe 1 or 2, something like that. Then I integrate that to get the total cooling, and that gives me this. And then I take the logarithmic derivative of that. And I get beta plus 1 over this difference between the surface temperature and the tropopause temperature. And if I evaluate that, well, this is like close to 200 Kelvin, this is about 300 Kelvin, so this difference is about 100 Kelvin. And if beta is 1 or 2, well, that gives me like 2 or 3% per Kelvin, right? Factor of 1 over 2 over, factor of 2 or 3 over 100 Kelvin, right? So that's a really simple model. What is it telling us? Well, this expression here on the bottom is actually the depth of the atmosphere measured in temperature coordinates. You can measure the depth of the atmosphere in many ways. In Z space, it's maybe 17 kilometers in just altitude, or it's maybe 900 hectopascal if you measure it in pressure. But in temperature, it's about 100 Kelvin. And let's say that this curve, instead of being linear quadratic, was just constant. Well, then Q would have to scale directly with the depth of the atmosphere. And the key point here is that if the atmosphere is 100 Kelvin deep and you increase the surface temperature by 1 Kelvin, that's a 1% increase in the depth of the atmosphere. So if the radiative cooling, the total cooling is scaling with the depth of the atmosphere, then it must increase at roughly 1% per Kelvin. And in fact, if it was constant throughout the depth of the atmosphere, I'd set beta equals 0, and I would get exactly 1% per Kelvin. So that's just the order of magnitude, and the fact that it's 2 or 3% per Kelvin and not 1 is just because beta is not 0, it's something like 1 or 2. So that gives you a way of understanding. All right, so coming back to our table here. So we built a simple model for mean precipitation change. This was written up in an article that came out in PNAS in November. And again, it's not just that you have a way of estimating it on a blackboard, but hopefully you learn something from it. And I think what this simple model is trying to tell us is that, at least as far as mean precipitation change is concerned with radiative cooling, you can think, if you think in temperature coordinates, you can see the atmosphere sort of deepening from the bottom down, and it's deepening in temperature coordinates at a rate of 1% per Kelvin roughly. And that's what sets the overall magnitude of this number. So that's all I have for today, and thank you for your attention.